Another thing that we can use the integrated rate laws for is to calculate the half-life of various chemical reactions. Imagine that you take a certain medication. If you don't know how long the half-life of that medication is, or when your next dosing period should be, it could build up in the body. So it's important to know how long it will remain active for before the body metabolizes it and breaks it down. This leads us into half-life. Half-life is given by T sub 1/2. It's the time required for the reactant concentration to drop to half of its initial value. We previously looked at the first order decomposition of hydrogen peroxide. If we start with 1 mole per liter of H2O2 and we drop the concentration to 0.5 moles per liter, that would represent the concentration falling by half. So that would represent the first half-life. The time it takes for it to fall from 1 mole per liter to 0.5 moles per liter is our T1/2. In this case, delta T is equal to 6 hours. So that first half-life took 6 hours. We could consider a second half-life, how long it takes for the concentration to drop from 0.5 moles per liter to 0.25 moles per liter. This would represent the second half-life. In this case, T1/2 of our second half-life also equals 6 hours, because the time lapsed, or delta T, was 6 hours for it to drop by half again. For hydrogen peroxide, we could consider a third half-life, the time it takes for the concentration to drop from 0.25 moles per liter to 0.125 moles per liter. This would represent the third half-life. In this case, delta T also equals 6 hours. So hydrogen peroxide is a first-order reaction. And we can see that for a first-order reaction, the half-life doesn't determine what the delta T is. No matter what we started with for our concentration, the time lapsed for half of it to go away was 6 hours every time. This will be true for any first-order reaction. The half-life of a first-order reaction can be calculated directly from the rate constant K. We saw that the half-life did not depend upon reactant concentration. When we look at our formula for calculating half-life, T1/2 is equal to 0.693, some constant value, divided by K, the rate constant. That'll be the time it takes for half of whatever initial concentration we start with to go away. There's no concentration term in this formula. We can actually start with our first order integrated rate law equation, ln of the concentration after some time divided by the original concentration is equal to negative K times T. If we solve for T, that would be equal to the natural log of the ratio of our concentrations divided by K, the rate constant. And we would have negative on the top. If we think about what it would mean for half of it to go away, we could say that we have negative ratio of some concentrations divided by K. Let's just pick two concentrations. Imagine that initially our original concentration was 2 molar, and then for half of that to go away, it would mean we drop down to 1 molar for our A sub T. Here we have negative ln of 1/2 over K. And if we call T T1/2, negative ln of 1/2 equals the natural log of 2 using rule of logs over K. And that will reduce down to 0.693 if you take the ln of 2. So that's where that 0.693 constant comes from, because it doesn't matter what concentration you start with or what you end with, we're always going to have 1/2 of that concentration remaining. So T1/2 formula can be derived directly from the first order integrated rate law. It does not depend upon the concentration, so you don't see any concentration term in your calculation. All you need to know is the rate constant K. Or we could also be given the half-life and solve for an unknown rate constant as well. We could also look at the first order half-life graphically. On the y-axis we have concentration, and on the x-axis we have time. So we're looking at that exponential decay of our reactant going away with time. And if we look at the half-life, that tells us how long it takes for half of it to decompose. So we started with 0.2 molar, And for half of it to go away would mean we would drop down to 0.1 molar. And if we count the squares, those will represent seconds. So it takes 1, 2, 3, 4, 5, 6, 7 seconds for the concentration to be cut in half from 0.2 molar to 0.1 molar. That's the first half-life. If we look at our second half-life, it would mean our concentration goes from 0.1 molar to 0.05 molar in this case. And so looking at our number of squares or our seconds, we count them again, it takes 7 seconds again for the concentration to be cut in half. Going from 0.05 down to 0.025 would represent our third half-life. And if we look at the time it takes 7 seconds again for our concentration to be cut in half. So for a first order reaction, graphically you can also see that the half-life is constant. No matter what concentration you start with, if you cut it in half, it will take the exact same time for that to decompose. Let's try an example calculation with first order half-life. The half-life of an isotope is 1.4 days. If you begin with 4 milligrams of the isotope, what quantity remains after 1 day? Assume first order. So in this case, we're given the half-life, or T1 half. We're told it's 1.4 days. We also know our initial concentration was 4 milligrams, so that's our A sub 0. And what quantity will remain after 1 day? 1 day would represent our time that's lapsed. We're trying to figure out A sub T here, how much will remain. So we're going to have to start with our T1 half equation in this case, because we were not given a K. We don't know the rate constant. So T1 half equals 0.693 divided by K. We can rearrange and say that T1 half times K would equal 0.693. And then if we solve for K, the rate law constant will be equal to 0.693 divided by T1 half. So we will take the ln of 2, or 0.963, divided by 1.4 days, because that was our half-life. And so our rate constant we get, or K, comes out to 0.495 days to the minus 1, so 1 over days as our units. Now that we used our half-life formula to figure out our rate constant, we could go back to our first order integrated rate law equation and solve for our concentration after some time has passed, just like we've done in other problems. So using the y equals mx plus b form to start, ln of a sub t will equal negative k times t plus ln of a sub 0, our original concentration. So ln of at will equal negative, plug in our K value we just found, 0.495 days to the minus 1, times our time. Our time was also given to us in units of days, so we don't have to convert it. 1 day has passed, plus the ln of our original amount, which was 4 milligrams. So we'll plug in 4 for our A sub 0. Everything on the right-hand side will come out to equaling some value. Don't forget your negative sign out front. So it ends up coming out to actually a positive value when you multiply everything and take the ln of 4. You should get positive 0.891. And then we have to undo the natural log function, so we're going to have to take e to both sides. That means the concentration A sub t will equal e raised to the 0.891 power. And we should get a value less than 4 milligrams because some time has passed, and it ends up being 2.44 milligrams that will remain after 1 day. So this combines the half-life formula with our first order integrated rate law. We have to use both of them for a first order type kinetics. We can't use the second order half-life or the second order integrated rate law if we have a first order reaction. There is a different half-life equation if we're dealing with a second order reaction. If we have a second order reaction, we can see that the T1 half will equal 1 over K times A sub 0, or the original concentration. So second order half-life does depend upon concentration that you're starting with. And you can see that that original concentration is in the denominator. So as that concentration gets smaller and the initial concentration goes down, the half-life will go up because you're going to be dividing by a smaller number and then dividing by another smaller number. So half-life will increase as you start to have your original concentration go down. If we look at a second order decay, once again we have concentration on the y-axis, time in seconds on the x-axis. You can visually see that the half-life is increasing as we go from the first to the second to the third half-life, and that's due to that concentration term being in the denominator. If you compare the second order half-life equation to the first order half-life equation, remember there was no concentration term, and so the half-life was constant throughout for first order. Whereas for second order, if we start with 0.2 molar and drop down to 0.1 molar, that would represent half of it going away, so your first half-life is relatively short. And then going from 0.1 molar down to 0.5 molar. Now if you look at the number of seconds or the length of this line, it's gotten longer, the half-life's increased. Going from 0.05 molar down to 0.025 molar, you can see that the half-life has grown even longer. It takes longer and longer for half of it to go away as it decomposes for a second order equation. The reaction 2HI, decomposing into H2 plus I2, has the rate law R equals K HI to the second order, with a K equals 0.079, 1 over molarity times seconds, at 508 degrees Celsius. What is the half-life for this reaction when the initial concentration of HI is 0.10 molar? Notice in the problem, nowhere did it say that this was a second order equation. We can figure that out though because we were given the rate law for the equation. We only have one species and it's raised to the second order here. So it must be an overall second order equation. So we're going to have to use our second order half-life. Also the units that are associated with K, 1 over molarity times seconds. That's also the units that will always be for a second order kinetics equation. So we have our K value. We also know our initial concentration, A sub 0, is equal to 1.01 molar. K is equal to 0.079, 1 over molarity times seconds. And so our half-life for a second order equation, T1 half equals 1 over K times our initial concentration. So all we have to do is substitute everything into that half-life equation. K, 0.079, 1 over molarity times seconds, and A sub 0 is 0.10 molar. When we solve, we'll end up getting T1 half to be 1.27 times 10 to the second, and the units will be seconds because those were the units on our rate law constant K.